Okay, gas stoichiometry. So you'll see here that I have set out the template of our mole train from our previous stoichiometry lessons. In Unit 3, we began with mass of one substance converted to amount in moles, and then to amount of a different reactant or product in the balanced equation, and finally to mass. How did we do that? Can you recall the conversion factors? What can you label above each of these three arrows here? Okay, so hopefully you recall molar mass converts from mass to moles, and so will the molar mass of substance A, whatever that is. We use the coefficients from the balanced equation as the mole ratio, and molar mass of the last substance, substance B, whatever that is. Okay, then in the solutions unit, we discovered the concepts of amount, concentration, and volume, and realized that we could convert to moles if we were given concentration and volume of a solution. So what formula would we use to find the amount of a substance, knowing the concentration and volume? Okay, so hopefully you recall N equals C times V. So in those types of problems, we started off with concentration and volume of a solution, found moles by N equals C times V, used a mole ratio to get to moles of another substance in the equation, and sometimes finished off with mass or perhaps volume or concentration. So either of these two formulas would be used, and the other variable would have been provided for you. Sometimes we had a concentration of a solution and we were asked for the concentration of ions, and in that case we had a bit of a shortcut. That's where we used the mole ratio, since we were really just talking about a solution of a substance and, for example, 0.1 moles per liter of calcium chloride, and if we knew that that was the concentration of the solution, then we could write a dissociation equation and work with the mole ratio. So for example, the chloride ion concentration would have been 2 times the 0.1, so 0.2 moles per liter. So what's happening now in terms of gases? Well, up here we have pressure, volume, and temperature. So if it's a gas that you've been given information about, you have the pressure, volume, and temperature, then isolate N in the ideal gas law, so PV over RT, in order to calculate moles. Once you have moles, you can move right along with mole ratio and then find whatever it is you're looking for, either the volume, pressure, or temperature of a gas that's being produced, the mass of a solid or substance that's being produced, or perhaps the volume or concentration of a solution. So the questions will not entirely involve solids or solutions or gases. I mean, occasionally they do, but you may in fact have all of them mixed together, and I'll make sure I do an example like that. For example, you could have a solid that's reacting to later on form a gas. You could have a solution that's reacting to later on form a solid. You could have a gas that's reacting to later on form a solution. There will be a shortcut type of question though in the gases unit, and that's where you've been given the volume of a gas of one reactant or product, and look to find the volume of a gas at another. And because of Avogadro's law, which we discussed in an earlier video, the mole ratio is actually the volume ratio. And so we can use, and I'll make sure to do an example of this, use the mole ratio as a volume ratio. This is based on experimental evidence first by Gay-Lussac, but later explained by Avogadro and supported by kinetic molecular theory. Okay, so on to a few examples. Okay, and so the first example, we're being asked what volume of water vapor is produced when 3 liters of hydrogen gas combines with excess oxygen gas. So as with all stoichiometric problems, you're being asked to relate information about one reactant or product to another, which requires a balanced equation. So start with your balanced equation for the synthesis of water vapor from hydrogen and oxygen. Okay, so you'll notice that I jotted down that balanced equation, and I also added into the question here that the information that all gases are at the same temperature and pressure. I've listed the given, the volume here at 3 liters of H2, excess oxygen, and we're being asked for the volume of H2O vapor produced. So if you recall back to the mole train here, we're really being given the volume of a gas, the hydrogen, and being asked to find the volume of another gas, and all the gases are at the same temperature and pressure. So that's important to add here. The gases must be at the same temperature and pressure. And when that's the case, then you can use the mole ratio as a volume ratio. So I'll show you what I mean here. We're going to use factor label just like we have in the past, finding the volume of the water vapor, starting with the 3 liters of the H2. And it's literally just a volume ratio, the same way you would use, so liters of H2, the same way you would do moles of H2 to moles of H2O, liters of H2 to liters of H2O. This only works with gases, and all the gases have to be at the same temperature and pressure. So we use the coefficients from the balanced equation as our volume ratio, and we can see that we end up with the same volume in this case because the ratio is 2 to 2, so 3 liters of water vapor. Okay, so that's an example of how you can use the law of combining gas volumes and Avogadro's law to very simply factor label mole ratio, but write the units of liters, and you'll find the volume of any gas, so stoichiometric amounts of gases in a reaction. Okay, example number 2. Here I'm asking you to determine the mass of ethanol that needs to be combusted to produce 350 mils of CO2 at SATP conditions. So again, start with a balanced equation. So think of the type of reaction that's happening here, predict your products, balance the equation, and list the given. And then stop there and check back with the video. Okay, so a balanced equation is written with the products of complete combustion. I'm looking for mass of one of the reactants, ethanol, and we're working from 350 mils of CO2 at SATP. So if I think back to the flow chart then, I am starting off with the volume, right, pressure and temperature of a gas, of the CO2. So I'm going to find first the amount of CO2, then use mole ratio to convert to the amount of ethanol, and then finish with the mass of ethanol using molar mass. So I'll be aware to convert my liters to, or my milliliters to liters here, and recall the SATP conditions of 25 degrees Celsius, which I'll need to add 273 to convert to Kelvin, and the SATP pressure at 100 kilopascals. I'll count this as 3 sig figs, by the way, since it's a defined standard. Okay, so first step, I'm going to be calculating the moles of CO2 by PV over RT. Second step, mole ratio. Third step, find the mass of ethanol. So try and work ahead and check back with the video. Okay, so as I was working through and eventually checking sig figs here, I noticed an error here. So this volume had 2 sig figs. That trailing 0 is not significant. And so when I converted, I should not have had a 0 here. So I've left this now as 2 sig figs. Okay, so N equals PV over RT, calculate the moles of CO2. Then mole ratio to convert the moles of CO2 to moles of ethanol. And again, I'm keeping extra digits past what I'm anticipating will be in the final answer. And then in the final step, I'm converting moles to, via molar mass, to mass of ethanol. Finishing with 2 sig figs because there's 2 sig figs in our volume, and that's the lowest we have through the calculation. You may have combined the last 2 steps, so perhaps just find mass by starting with these moles, string the mole ratio, and then the molar mass, this conversion factor right up beside here. That would be totally fine. Or perhaps you use the formula to find mass in the last step instead of factor label. Of course, that would be fine too. Okay, so one last question. I'll look to do a problem where I combine grams, concentration, volume, and ideal gas law all in the same question. And I'll throw in limiting reactant just to help you review that. Okay, so I'm asking you to determine the volume of H2 gas produced at 22 degrees Celsius and 102 kilopascals when 0.25 grams of magnesium ribbon reacts with 125 mils of 0.100 mole per liter hydrochloric acid. So I'm expecting that you're going to give this a shot on your own before seeing how it's worked out in the video. Again, this is all familiar at this point. So start with your balanced equation, list the given, identify the limiting reagent, determine the moles of hydrogen gas produced from the moles of limiting reagent that you have that is reacting, and then determine the final answer, the volume of H2. So I've balanced the equation, listed my given, and I'm recognizing here that I need to find moles of magnesium and moles of the hydrochloric acid, determine which is limiting, so that I'll know which one to use to get the moles of H2. I'll finally finish with V equals nRT over P to have my final answer. So I have determined the moles of magnesium and the moles of acid that I have to start with. Now I'll find the stoichiometric amounts to see which one is limiting. Okay, so it turns out that the acid is the limiting reagent because I'll need 0.02056 moles of acid to react all of the magnesium, and in fact I only have just over half of that. And so HCl is limiting, so I'll use the moles of the limiting reagent that I have and the mole ratio to determine the moles of hydrogen gas that will be produced. Final step, to find the volume of the hydrogen gas produced. Now that I know N, I always know R, T and P were given. We did our conversions to Kelvin and we're good to go. Okay, and so substituting in, I finish with 0.150 liters. So that's showing 3 sig figs, and if I track them back through, really what I ended up using in the calculation were the moles of acid here. That came from 3 sig figs, 3 sig figs. I have 3 in the Kelvin temperature and pressure, which I'll be plugging in later into V equals nRT over P, and so I'll finish with 3 sig figs. So there you go, that's everything put together. Good luck with that.